Hey everyone, and welcome back to The Explainer. Today, we're digging deep. Well, actually, scratch that. We're going to focus on staying remarkably close to the surface. We're exploring the fascinating world of geotechnical engineering, specifically focusing on Chapter 15, Shallow Foundations. I'm just endlessly curious about the hidden infrastructure right beneath our feet. We walk into towering skyscrapers and massive structures every single day, completely oblivious to the incredible, highly calculated science happening just inches below the ground we step on. So today, we're going to illuminate that hidden world. It really all starts with a high-stakes question. What keeps a massive building from just sinking right into the earth? It sounds like a simple physics problem, but the ground is incredibly dynamic. Without proper, precise engineering, we face absolutely disastrous consequences. The entire structure of our built environment relies on battling two primary enemies: catastrophic shear failure and something called detrimental settlement. Basically, if the engineers get it wrong, the building either comes down or it slowly tears itself apart. So here's our blueprint for today's explainer. First, the foundation of it all. 2, shallow versus deep. 3, the world of spread footings. 4, rafts and floating. And finally, number 5, match soil to structure. All right, let's jump right into section 1, the foundation of it all and the 2 golden rules. Okay, so it's absolutely crucial that every foundation rests on these 2 golden rules. First, it has to prevent shear failure. In geotechnical terms, this means stopping the plastic flow of the soil material. You literally cannot have the soil underneath the foundation being laterally expelled, essentially squishing out from underneath the heavy load of the building. Second, the foundation has to limit detrimental settlement. Now, a little bit of sinking is natural, but the anticipated settlement, both the total amount and the differential sinking across the building, has to be kept to a safe, tolerable magnitude. Otherwise, it destroys the stability of the whole structure. Moving right along to section 2, shallow versus deep, and Terzaghis rule. To define the line between shallow and deep, we turn to Terzaghis rule. Carl Terzaghi was a massive figure in soil mechanics, and he came up with this wonderfully simple mathematical ratio. He stated that a foundation is considered shallow if its depth is equal to or less than its width. If the depth exceeds the width, well, then it's classified as a deep foundation. It's kind of crazy how such a simple ratio defines these massive engineering choices, right? It's a really simple visual concept. Imagine the horizontal width, we'll call it B. If that width stretches out further than the vertical depth goes down into the soil, boom, you have a shallow foundation. These simple dimensions completely dictate the bearing capacity theories that engineers are going to use to keep the building standing tall. All right, section 3, the world of spread footings, which are essentially massive structural pads. If we look at the whole geotechnical family tree, shallow foundations branch off primarily into spread footings on one side, and things like combined footings and rafts on the other. Under spread footings, they break down even further into continuous footings for long walls or isolated footings for single columns. It really gives you a sense of the toolkit engineers have at their disposal. So, what exactly is a spread footing? Essentially, it's a giant structural pad. Think of it like putting on a snowshoe. If you walk in deep snow in normal boots, your concentrated weight causes you to sink right in. But a snowshoe spreads that exact same weight over a larger area so you float on top. A spread footing does exactly this for a building. It takes the massive load from a column or a wall and spreads it over a sufficiently large area of foundation soil. And these are usually constructed as close to the surface as possible, but safely below the frost penetration depth and away from the risk of soil erosion. And engineers don't just have a one-size-fits-all solution for this. There are several common variations of isolated spread footings they can choose from based on the job. You've got plain or simple footings, mass concrete footings, which are typically used for steel columns, sloped footings, and stepped footings. The engineer carefully chooses the exact shape and variation based on the specific load of the column and the actual space constraints of the site. But what happens when the ground isn't perfect? Often, the topsoil has totally inadequate bearing capacity. It's just too soft or unstable. Engineers obviously can't just put the footing on bad soil. So they dig down to the soil or rock that actually has adequate bearing capacity. Then, to bridge the gap back up to where the footing needs to be, they use either a lean concrete pad or heavily compacted sand and gravel. It's a really clever, practical adaptation to tricky terrain. Which brings us to section 4, rafts and floating in deep compressible soil. Now, when you're dealing with deep deposits of highly compressible, cohesive soils, situations where the ground is basically too soft and standard piles are just impractical, engineers turn to the floating foundation. And this isn't just a physical type of foundation, it's a brilliant engineering concept. They assemble a combination of a raft and a caisson to create a rigid box underground. The magic here is that they excavate an exact amount of soil whose weight perfectly equals the weight of the new building. By doing this, the stress on the deep soil remains exactly the same as it was before the building was even there. The building is literally floating in the earth. No extra stress, no sinking. Finally, let's hit Section 5. Match soil to structure. It's the ultimate engineering matchmaking game. Matching the soil to the structure involves some really complex decisions. If you have beautifully compact sand or firm clay extending deep down, you're in luck. Spread footings are your most appropriate and conventional choice. But look what happens when you introduce soft clay. A spread footing might work if it's a light load, but a heavy load absolutely demands deep foundations. And if you're building on loose sand extending to great depths, spread footings will just settle way too much. In that case, you have to switch to a raft foundation, drive piles, or artificially compact the sand first. So it all comes down to a comparison between shallow and deep. Shallow foundations, particularly spread footings, are the most widely used simply because they are the most economical. They require the least amount of heavy equipment, and engineers can easily inspect the soil right there at the surface. Deep foundations, on the other hand, are strictly deployed when the soil has incredibly low bearing capacity, or when the sheer massive load of the structure requires you to entirely bypass those weak upper strata to find solid rock way below. Which brings us to this final thought. The next time you walk into a towering building, just take a second and look down. Ask yourself, what exactly is the soil doing beneath your feet right now? Is a massive spread footing acting like a snowshoe to keep you afloat? Or is the entire building perfectly displacing the weight of the earth, floating in a rigid box of concrete? The invisible math and structure beneath us is just as fascinating as the architecture towering above us. Thank you for joining me on this explainer, and keep questioning the world beneath your feet.